Hello everybody, my name is Jason Halliday and my partner is Devin Hoskins. Our ECE591 final project presentation is about utilizing the VIT-Adapter for semantic segmentation. The main inspiration for this project is a paper called Vision Transformer Adapter for Dense Predictions by Chen et al. That explores the use of the vision transformer for dense prediction tasks by using an external training-free adapter that introduces image-related knowledge to a pre-trained VIT. The goal of this paper was to close the gap between the classic VIT, which utilizes a classic transformer encoder, and vision-specific transformers for dense prediction tasks. The plain VIT commonly struggles with dense prediction tasks. Examples of vision-specific transformers include the Swin transformer and pyramid vision transformer, which involved a heavily modified form of the vision transformer, which is specific to images for inputs. The motivation for using a plain vision transformer is the fact that it can train on multimodal data like video, image, and text, which makes it easier to train and encourages semantic-rich representations. In other words, the VIT allows for a higher number of features that can be correlated with a given input. For this project, we used the VIT-Adapter Tiny model, which had the smallest number of learnable parameters and required the least computation of all the VIT-Adapter models. The VIT-Adapter is split up into two parallel paths, the vision transformer and the adapter. The vision transformer takes the input image and breaks it up into 16 by 16 pixel patches and linearly embeds each patch into a one-dimensional vector called a token. These tokens are positionally embedded before being passed through the first three encoder layers. The adapter uses the spatial prior module to convolutionally extract features of three different sizes. These features are then passed to the feature injector, where cross-attention is performed between the patch embeddings from the VIT and the spatial priors that have been extracted by the spatial prior module. The result of this interaction is injected into the patch embeddings before entering the first block of encoder layers. After each encoder block, features are extracted and cross-attention is performed once again to build on the spatial priors. The result of the cross-attention is passed through a feed-forward network. This entire process is called a feature interaction. Feature interactions occur for every encoder block in the system. In the case of the VIT Tiny that was used, there are 4 blocks of VIT encoding and 4 feature interactions. Each encoding block has 3 encoder layers. Therefore, there are a total of 12 encoder layers into the model.
For our project, we proposed testing the transfer learning ability of the VIT-Adapter large model to a dataset that we found on Kaggle.com called Semantic Segmentation for Self-Driving Cars. The VIT-Adapter L, or large, is the state-of-the-art model for semantic segmentation on the Cityscapes dataset. We then proposed to use fine-tuning to attempt to improve the performance on the Kaggle dataset. As a new model, it is important to be accurately transferable to other datasets, especially when the application is for something such as autonomous vehicles, where mistakes are quite unacceptable. We did have some issues with this initial proposal, so unfortunately we were unsuccessful in implementing the VIT-Adapter model on the Kaggle dataset. First of all, setting up the environment in which we could even test the model took a majority of our allotted time. We are also using Colab, which was a challenge in itself. We were using PyTorch for the first time. That's what this model was written in, and so that was a bit of a learning curve. And it was also challenging to figure out which versions of packages we needed to install because Segmentation is pretty picky when it comes to the versions of packages to use. And the VIT-Adapter models use or modify the segmentation framework for their models. The complexity of the data set and models made it challenging to navigate and make the required changes in order to get a pre-trained model to test. And it was even more challenging to get it to test on a new data set. So eventually we were able to test the VIT-Adapter large on the Cityscapes data set, which it was the state of the art for the Cityscapes semantic segmentation, and this test alone took around 10 minutes per image, so a lot more time than we had. So after a couple of weeks of working through some of these issues and consulting with Professor Yifeng, it was decided to change our goal for the project. So after some thought, it was decided that a new proposal for the project would be considered. First, we decided to get away from the idea of transfer learning for this model, as setting up a new data set in this framework would be very time consuming, and we'd quite possibly unsuccessful doing so. So we decided to due to a time constraint, that we should investigate using a smaller model, which meant we would have to forget using the state-of-the-art model for semantic segmentation on Cityscapes, as the large model was the only one they had for that. So we found the VIT-Adapter Tiny for semantic segmentation, which was pre-trained on the ADE20K dataset. The new proposal was to make changes to hyperparameters in this model, and then train the model with the new parameter changes and analyze the performance based on the hyperparameters that were changed.
Looking at the VIT-Adapter Tiny configuration file, there are plenty of hyperparameters to make adjustments to. For this project, we will be looking into a few of them to see how the model performance is affected. We investigated the following hyperparameters: number of heads in multi-head attention, number of heads in deformable attention, and the feed-forward network size. Initially, we were interested in the number of feature interactions and the number of encoder layers between each interaction, but due to time and complexity, we were not able to get this hyperparameter to work outside of its default values. The dataset used for this project is called ADE20K. The dataset consists of a total of 20,000 images, 18,000 of which are training and 2,000 for validation. It contains 150 classes, some of which are entire objects, others are considered parts of objects. For example, a car might be the object, but the car also has doors that can be identified. The main reason for using this dataset was that a pre-trained VIT-Adapter Tiny model was available as a baseline. This made it easy to make modifications and have a logical comparison to. Another reason why this dataset was selected was because the framework we wanted to use, called Segmentation, natively supported this dataset, making it easier to set up compared to a custom dataset.
For each hyperparameter that we wanted to change, we would first modify the VIT-Adapter T models.py file with the desired parameter, and then train on 5,000 images. We had to make a new scheduler file to train for 5,000 images because the smallest training set they had was 20,000 images, which took more than 4 hours to train. And we didn't have time to do that for each modification. Once we trained the model, we ran an evaluation test on it, which resulted in intersection over union and accuracy for each class. It also gave a summary for pixel-wise accuracy, AACC, IOU, and average accuracy, or MACC. As a result of training on such a small data set, many of the classes that ADE20K has were not represented in the training set, which resulted in many classes with 0 accuracy and 0 IOU. For our results, we looked at the pixel-wise accuracy so that the classes with zeros were not taken into consideration. Next, I will give a little background information on deformable attention, which is the first parameter that we'll look at. In a paper written by Shaw et al. Titled Vision Transformer with Deformable Attention, they proposed deformable attention to mitigate the issues of high computation costs in creating feature maps with influence from relevant parts beyond regions of interest. For each attention module, reference points are first generated as uniform grids, which are the same across the input data. Then an offset network takes the query features as an input and generates the corresponding offsets for all the reference points. This shifts the keys and values towards important regions. This image represents some different applications of attention for transformer models. Figure A is the plain VIT, which learns full attention for all queries. This can be a large use of computational power. The Swin transformer in Figure B attempts to avoid this excessive computation when using attention, but has likely dropped some relevant features in the process. Figure C shows the implementation of the deformable convolution network, which learns different deformed points for each query. Finally, Figure D shows the deformable attention transformer, which learns shared deformed points for all queries and is very focused on the relevant features of the input image. The first parameter that we modified in the model was the number of heads in deformable attention. Deformable attention is the type of attention that was used for the adapter. For each feature interaction, which was always set to 4 in this paper, deformable attention was used for both the feature injector and feature extractor. The default number of attention heads for the VIT-Adapter Tiny was 6, so the middle plot is the default model. We then tried both decreasing the number of heads to 4 and increasing to 8. Surprisingly, as shown here in this plot, the default configuration of 6 attention heads performed the worst of the 3. Increasing the number of heads to 8 did increase the performance as expected, but decreasing the number of heads to 4 also increased the performance from the default, which surprised us. 8 heads performed the best at 44.69% accuracy, while 6 and 4 heads had 43.41 and 44.5% accuracy respectively. It would be interesting to test different configurations such as maybe 12 or 16 heads to see if the accuracy continues to increase when you increase the number of heads, or if at a certain point extra heads just become redundant.
In order to test how the number of heads in multi-head attention affects segmentation accuracy, 4 configurations of the VIT Tiny were used, each with a different number of heads for multi-head attention. The default model uses 3 heads, so we tested other configurations with 1, 2, and 4 heads for comparison. The results show that the model with 4 heads performed the best with a pixel-wise accuracy of 44.9%. The default configuration with 3 heads performed the worst with an accuracy of 43.41%. The single head and 2 head configurations performed just about identically, getting 44.36 and 44.37% accuracy respectively, outperforming the default configuration. The expected trend was that as we added more heads, the accuracy would improve, but the 3-head configuration breaks that trend. The last parameter that was tested was the FFN ratio. The VIT-Adapter Tiny module utilizes a token length of 192. The feed-forward network ratio is a ratio of 192, so a ratio of 0.5, for example, will give a FFN size of 96. The bigger the feed-forward network, the more learnable parameters the model will have. The 4 configurations we tested had FFN ratios of 0.125, 0.25, 0.5, and 1. The default configuration had a feed-forward network ratio of 0.25. The best configuration, based on our tests, was the model with an FFN ratio of 0.5. It had a pixel-wise accuracy of 44.44%, closely followed by the FFN ratio of 1 configuration with an accuracy of 44.41%. The worst performing model was the default feed-forward network ratio of 0.25 with an accuracy of 43.41%. The model with the smallest FFN ratio achieved an accuracy of 44.25, which was surprising. We encountered lots of challenges with this project, some of which we were able to figure out. Other challenges result in a slight change of plans. The first challenge was Google Colab. Compared to the authors of the VIT-Adapter who had a GPU cluster, we were restricted to a very limited amount of time with one of Google's GPUs. To train one VIT-Adapter Tiny configuration on 5,000 images, it took over an hour. If we were to try and replicate what the authors of the model did and train our model for 1.6 million images, it would have taken over 400 hours per configuration. Keep in mind, this is the smallest version of the VIT-Adapter. The next challenge was that every time we wanted to use our model, the environment needed to be reset up and the dataset needed to be downloaded and unzipped, which can take up to 20 minutes. The next challenge we faced was with the segmentation framework. Although the framework definitely made segmentation possible for this project, it had a fair share of challenges, including high complexity for setting up a custom dataset, which was one of the initial goals of this project. The last major challenge we faced was the lack of documentation on our specific model. Some of the hyperparameters would cause errors when changed, making it hard to test the parameters that we were interested in, like number of feature interactions. So we got some demos using the VIT-Adapter Tiny. As you can see, we took an image of the UMaine Mall, and it was successfully able to capture all the people in the mall, highlight the trees in color, and highlight the building and sky as well. This demo is a busy street scene, and it captures various bikes, buses, cars, trees, sidewalks successfully. This is an aerial shot of the UMaine campus, and it's successful in highlighting all the buildings, highlighting some sky, the water, and all the trees as well.
To summarize our overall results, you can see that the multi-head attention using 4 heads performed the best out of any models that we tested, with an accuracy of 44.9%. This was the attention that was used in the plain VIT, not in the adapter. What really threw us for a loop was the fact that the default model that they were running by our testing performed the worst out of all the modifications that we ran. This could be some kind of user error on our part, but it was still very surprising. You'll also notice at the bottom of the table, there is a model that achieved 80.27% accuracy. This is the results that the developers of the VIT-Adapter achieved by training with 160,000 images 10 times through. That just goes to show that with more computation power in time, our results would have performed better and possibly more consistent. Given more time and resources, there is a lot of work that can be done on this project. First, to achieve more accurate results, it would be necessary to take the time to train the model on a much larger data set. This way, the model would see all the classes that it missed in the small data set that we gave it. It could also possibly provide more consistent results. We'd also like to test models with a greater number of heads in both the VIT attention and the adapter's deformable attention. It would be interesting to find if there's a point at which extra heads for attention becomes redundant, and if there's a maximum number of heads that provides a maximum performance. We would like to explore more hyperparameters to change in the models, and we could also look at different combinations of parameter modifications. It would be desirable to figure out how to test the model with a different number of blocks or feature interactions, since that is a core aspect of the adapter. There's probably a reason that the researchers used 4 blocks for each of the models, but it would still be cool to test different numbers of interactions and/or encoder layers. Increasing or decreasing these blocks and encoder layers would most likely change the computation time and performance, but we were unable to make these changes work, so that would be something we'd like to try in the future. Finally, with more time and resources, it would be desirable to go back to our original proposal of testing and fine-tuning for transferable learning. As mentioned before, it is an important aspect of a new model, especially one that can be used for autonomous vehicles. All right, thank you to anyone who listened to our presentation, and if anybody has any questions, you can drop them in the Piazza discussion. Thanks again.